Hello friends, welcome to Chandu Smart Class. This is Chandu. In this session we are going to discuss about DES, Data Encryption Standard. So it is a symmetric block cipher. It is a symmetric block cipher and it is published by NIST. NIST means National Institute of Standards and Technology, and initially in 1973 IBM designed an algorithm DES which came from the modification of existed algorithm Lucifer. The old name for DES is Lucifer. It is modified by the IBM to DES and it is published by NIST, National Institute of Standards and Technology. After that, some critics has been done on DES. Mainly there are two reasons. First one is key length. The key length of the DES is very small, that is 56 bits, so it is vulnerable to brute force attack. And second one, the internal structure of DES, which has a trapdoor for attacking. It is identified by National Security Agency. Okay. So based on these two reasons, some criticisms has been done on DES. After that, IBM modified the DES and improved the security of DES. The final version of DES was released in 1977. After that, it has become most popular symmetric block cipher, most popular cryptographic algorithm in 1970s. After some time, they improved the security based on the key length and has developed 3 DES, triple DES, which contains DES 3 times. So 3 ciphers are there in the 3 DES and the key length will be increased. Okay, this is the history of DES. Most importantly, it is a symmetric block cipher. So we already discussed about block cipher. The block cipher means the plain text will be divided into blocks and it will be encrypted at a time and ciphertext will be generated. Plain text will be divided into blocks and each block will be encrypted and generate ciphertext. Okay, and each and every character in the block contributes in the encryption of other characters. That is the phenomenon of block cipher. The encryption will be done in the plain text blockwise. Okay, so before going to the basic structure of DES, first we need to discuss about the basic terminologies. So it is a block cipher. So what is the block size of DES? Block size is 64 bits. Okay, 64 bits plain text. Plain text will be divided into blocks and each block which contains 64 bits. And next thing, round. So here we need to use Feastel cipher, Feastel structure as the round function. Each round is a Feastel cipher and there are number of rounds. Number of rounds are 16 number of rounds are there and each round which contains Feastel structure, Feastel cipher. We will know about Feastel structure later. And cipher key that is 64 bits and round key size is 48 bits. 64 bits will be divided into 16 48 bit keys. Those are sub keys. we need to generate the 16 48-bit keys, and each 48-bit key will be given as input to each round. So for total 16 rounds we need to give 16 48-bit sub keys, that is called round key. Okay, so block size is 64 bits, 64 bits plain text, and generate the 64-bit ciphertext also. Okay, 64-bit plain text and generate the 64-bit ciphertext. Here we need to perform the data encryption standard DES in 16 rounds. So each round has a physical structure. The key size is 64 bits, and for each round we need to give a round key, that is sub key. The length of the sub key is 48 bits. We need to generate 16 round keys from 64-bit cipher key. Okay, so these are the basic things we need to know before going to actual procedure of DES. So this is the general basic structure of DES. So here we need to give 64-bit plain text. The total plain text will be divided into blocks. Each block size is 64 bits, and the first function is initial permutation. So initial permutation means transposition. So we need to rearrange the position of characters in the 64-bit plain text. Initial permutation. After that we need to give the output of initial permutation to round 1. The output is also 64-bit round 1. So we need to give 2 inputs for all the rounds, 64-bit and 48-bit key. 48-bit key will be generated using round key generator, which has input 56-bit cipher key. So actually we need to give 64-bit. From 64-bit we need to generate the 56-bit cipher key. So later we will see the procedure. So like this we need to perform 16 rounds. So after 16th round the final permutation will be there. So this is also called as inverse of initial permutation. So whatever the permutations we are using in this DES, all the permutations are predetermined. The position of the characters. So permutation means transpose the position of the characters. We need to change the position of the characters. All the positions of the characters are predetermined by the DES designer. So after final permutation we will get the 64-bit ciphertext. This is the actual procedure. Here we need to know about each and every component, initial permutation and final permutation. These two come under a single point, and rounds and key generator. So round key generator. So first one, initial permutation, initial and final permutation steps. So here permutation means changing the position of the characters. Changing the position of the characters. So you can observe here from this diagram, 58th bit will become the first bit in the initial permutation, and first bit will become 48th bit. Like this we need to change the position of the 64 bits. After that we need to perform 16 rounds, and this is the final permutation. After 16 rounds we need to perform final permutation. It is inverse to initial permutation. So here initial permutation, 58th bit will become the first bit, and in final permutation first bit will become the 58th bit. Okay, so that's why it is called inverse of the initial permutation. So all these positions, 58th bit will become first bit will become 48th bit. All these positions determined by DES designer. All these are predetermined. This is the table of initial and final permutation. So 58th bit will become the first bit, and 58th bit will become the second bit, 42nd bit will become the third bit. Like this 64 positions are predetermined, and final permutation 48th bit. 48th bit will become first bit. Okay, so this is about initial and final permutations. And next thing we need to know about round. So each round has Feastal structure. This is the Feastal structure or cipher or design. Okay, so this is called Feastal structure or Feastal cipher or Feastal design. In Feastal cipher, the input will be divided into two halves, left half and right half. So here we need to give 64 bits. 64 bits will be divided into two halves, 32 bits, 32 bits, and on the right half you need to perform the function. You need to apply the function on the right half, f of r I minus 1 comma k1. So here this is called a round function. This is called a round function. This is the main part of the DES. The heart of DES is function. So to this function we need to give two inputs, right half and round key. This is called round key, and the round key size is 48 bits. Okay, and this is 32 bits. Okay, the output of the function is 32 bits. Each round has two components, mixer and swapper. The mixer which contains function. The output of the function and the left half, XOR, and the output of XOR operation will become the right half, and the previous right half will become the left half, and this is the input to next round. Okay, the right half will become the left half using the swapper. Second component in the round function is swapper. So swapping of two halves. So the output of XOR operation will become the right half, and the right half of the previous input will become the left half. So this is the Feastal structure. Each round has Feastal design. Okay, each round follows the Feastal design. Like this we have 16 rounds. We have total 16 rounds. So here we need to know about the function. This is the heart of the DES. We need to know about this function. So swapper, we know about the swapper, just exchanging the two halves, and mixer, here another operation is there, XOR operation. So already we know about XOR operation. So here we need to know about the function, round function. Let us see the round function. So this is the round function, DES function. This is heart of the DES. Here we need to give 32 bits, right half of input 32 bits. We need to perform expansion P box. In previous session we have already discussed different types of P boxes. So this is one type of P box, expansion P box. Here the number of inputs are less than the number of outputs. Expansion, expanding the number of bits. Okay, so 32 bits will become the 48 bits. So expansion P box means we are giving 32 bits input and getting 48 bits output. Okay, so that 32 bits will become the 48 bits. That is, the number of bits are increasing. That's why it is called expansion P box. P box means permutation. Okay, while increasing the number of bits, we are going to permute, transpose the position of the characters. That is expansion P box. And XOR operation we already know, 48 bits and round key 48 bits. So these two inputs will be given to the XOR operation and we will get 48 bits, and 48 bits will be divided into 8 parts. 8 parts. So 48 bits will be divided into 8 parts. So 48 divided by 8 is equal to 6. These are all S boxes. 8 S boxes are there. 48 bits will be given as the input to 8 S boxes. So each S box has input 6. Okay, each S box has input size 6 bits and the output is 4 bits. So total 8 S boxes are there. 8 fours 32. Okay, so 48 bits will become 32 bits with the help of S boxes. So 6 by 4 S boxes we are using. So each function has 8 S boxes. 8 6 by 4 S boxes, and last one is straight P box. So straight P box means permutation box. So all these permutations are predetermined. So the position of the characters already predetermined, 32 bits, and the output is 32 bits for straight P box. Okay, so first expansion P box. How we need to perform expansion P box? So this is expansion P box. So expansion means increasing the number of bits. So 32 bits will become 48 bits. So this is the procedure. So total 32 bits will be divided into 8 parts. 1, 2, 3, 4, 5, 6, 7, 8. Total 8 parts. So 32 by 8 is equal to 4. So each part size is 4 bits. So here we need to write 4 bits as it is, and first bit and sixth bit. First bit and sixth bit. First bit and sixth bit will come from previous and next parts. Okay, so here suppose if you take the second part, you need to write all the 4 bits in positions 2, 3, 4, 5, and first and sixth positions. In the first position we need to take the fourth bit of the previous part, and at sixth position we need to take the first bit of the next part. Okay, like this we need to perform for all these parts. For first part we need to take the last bit of the last part into the first position. Okay, so from bit 32, that is last bit of the last part will become the first bit in first part. Okay, so this is the expansion P box. So total 4 inputs and 6 outputs. So like this we have 8 parts. 8 into 6, 48 bits. So this is the expansion P box table. 1, 2, 3, 4, 5th bit. So we have 5th bit 2 times. Okay, 9th bit 2 times. 13th bit 2 times. Okay, so this is the expansion P box. 32 bits will become 48 bits. After that we need to perform the XOR operation of the output of expansion P box and round key. Okay, and the output of XOR operation will give as input to S boxes. These are the S boxes. Here 48 bit is the input to this array of S boxes. So total 8 S boxes are there. For each S box the input size is 6. So total 8 S boxes, 48 divided by 8 is equal to 6. So for each S box the input size is 6, the output is 4 bits. Okay, so this is the internal structure of each S box. Here the first bit and sixth bit are representing row number, and second through fifth bit representing column number. So total 4 rows and 16 columns are there. Each S box, so total 8 S boxes are there. 8 S boxes are there, and for each S box the size is 6 by 4, 6 inputs and 4 outputs. So out of 6 inputs, first and sixth bit are using for row number. Okay, and second, third, fourth, 5. Okay, 2, 3, 4, 5 bits are using for column number. The size of this table, S box table, is 4 by 16. 4 rows are there and 16 columns are there. Okay, so this is S box 1. All these values, whatever the values we have in this table, all these are predetermined. So 4 rows and 16 columns, and each row contains 16 values. Each row contains 16 values. Okay, 1, 2, 3, 4, like this we have 16 values. So 16 into 4, 64 values are there. Okay, so like this we have total 8 S boxes. S box 1, S box 2, S box 3, and so on. So total 8 S boxes are predetermined. Let us see a simple example. For example, input to S box 1 is 1, 0, 1, 1, 1, 0. Okay, and what is the output of S box 1? You need to follow this table. First bit and the last bit we are taking as row number. 1, 0 means 2, and 0, 1, 1, 1. Second bit, third bit, fourth bit, and fifth bit. These 4 bits for representing column number. 0, 1, 1, 1 means 7. Okay, so third row and 8th column, that means 1, 0, 0, 1, 1, 1. This is the substitution value, that is 1, 1. 1, 1 means 1, 0, 1, 1 in binary. Okay, so you need to substitute 1, 0, 1, 1 in the place of 1, 0, 1, 1, 1, 0. Okay, you need to do this process for all the 8 S boxes. Okay, after that we need to perform straight P box. So this is straight P box. So 32 bit by 32 bit. Okay, straight P box, 32 bits is input and 32 bits is the output. So all these values are predetermined. 16th bit will become the first bit, 7th bit will become the second bit, 28th bit will become third bit. Like this we need to follow this table blindly. Okay, so this is about the DES function. So expansion P box, expanding the number of bits. 32 bits will become 48 bits, and after that we need to perform the XOR operation on output of the expansion P box and the round key. We are using the round key here only. Okay, and the output of the XOR operation will be given as input to 8 S boxes. Okay, so the output of the S boxes, all the S boxes is 32 bits, and the 32 bits will be given as the input to straight P box. After that we get 32 bits, that is the output of DES function. So like this we need to perform in each round. Okay, so this is DES cipher and reverse cipher. So this is the internal structure of DES. Initial permutation is there, and next 16 rounds are there, and finally final permutation. So here DES define 2 approaches. So first approach is this design. So first design of DES, and alternate approach. So alternate approach is, so if you observe this, round 1, round 2, round 3, and so on, round 16. So total 16 rounds are there. So you can observe 16th round is different from other 15 rounds because the last round does not contain the swapper. Each round has 2 components, mixer and swapper, except 16th round. So why? Because to make cipher and reverse cipher designs same. Okay, so to make cipher and reverse cipher designs same, the 16th round does not contain the swapper component. So in the reverse cipher we have the mixer, and the cipher, the last round contains the only the mixer, does not contain the swapper. And in reverse cipher the first round contains mixer, so both are at same level. So to make the both designs, the cipher and reverse cipher designs same, first approach has been designed, and alternative to this first approach is to make all the rounds same. So we are adding two swappers in between round 16 and final permutation. By applying two swappers, there is no change in the bits. Round 1 to round 16, all the rounds follow the same structure, and we are adding extra swapper in between round 16 and final permutation. Okay, there are two approaches. First approach, this is the first approach, and alternative approach is adding two swappers after round 16. Okay, so alternative approach is used to make 16 round designs same. Okay, this is about DES cipher and reverse cipher. The most important one is key generation. So the cipher key size is 64 bits. Okay, so from this 64 bits we need to generate 16 48-bit round keys. So this is the procedure to generate the round keys. So 64-bit cipher key will be given as input to parity drop permutation table. This is parity drop permutation table here. So from this design of this box, you can observe that this is compression P box. So parity drop means 64 bits 1 2 3 4 5 6 7 8. You need to arrange all these bits like this: 9 10 11 12 13 14 15 16 and so on 64. Okay, we need to drop all these bits. These are called parity bits. We need to drop all these bits: 8th bit, 16th bit, 24th bit, 32 bit, or like this. We need to drop all these 8 bits. Total 8 bits we need to drop. So from 64 we need to drop 8 bits. The result is 56 bits. Okay, and these 56 bits must be permuted. Permutation means transpose the position of the characters. Okay, this is also predetermined. Okay, so that's why it is called parity drop permutation, parity drop P box, compression P box. Okay, so after that the 56 bit will be divided into two halves, 28 bits and 28 bits, and for each 28 bits we need to perform a circular left shift. We need to perform circular left shift operation. Okay, and 28 bits and 28 bits, so left half and right half, we need to perform a circular left shift operation, and after that we need to combine these two parts, 28 bits and 28 bits, and we need to give 56 bits as input to compression P box. It will convert 56 bits to 48 bits. Okay, compression P box, the size of output is less than the size of input. The number of output bits are less than the number of input bits. So 56 bits will become 48 bits, and that is the round key. Okay, and whatever the left half is there, that will be given as the input to circular left shift, and right half will be given as input to circular left shift operation. Okay, like this we need to perform 16 times. Okay, we need to perform circular left shift operation 16 times. For all the rounds, the number of bits will be different. Okay, so 1, 2, 9, 16. So first round, second round, ninth round, and 16th round. For these 4 rounds, the number of bits need to be shifted is 1 bit. Okay, for all other rounds, we need to shift 2 bits. So 1 bit shift operation for 1, 2, 9, and 16 rounds. Okay, 4 rounds, 1, 2, 9, 16. For these 4 rounds we need to perform 1 bit circular left shift operation, and for all other rounds we need to perform 2 bits circular left shift operation. So this is parity bit drop permutation table. This is parity bit drop permutation table. Here we need to drop all the parity bits, that is 8, 16, 24, 32, like this until 64. Okay, so we will get total 56 bits, and these are the total 56 bits. All these are permitted. Okay, so this is compression P box. This is compression P box. 57th bit will become the first bit, 49th bit will become the second bit, 41st bit will become the third bit, like this. These positions are predetermined, and the number of bit shifts. So first round and second round, ninth round, and 16th round. These 4 rounds, 1 bit circular left shift operation, and for all rounds we need to perform 2 bits circular left shift operation. Okay, and this is compression permutation table. Compression means the number of output bits are less than the number of input bits. That means we need to remove some bits, we need to remove some input bits, so we will get reduced output bits. That is compression P box. Okay, this is about key generation process. I hope you understood. So if you learned something from this video, please like, share, and subscribe. Thank you. Thanks for watching.